Okay, hello. I hope you're doing fine. So the target was chapter 2. There is one section, 2.3. So I'm going to summarize this section for you. This section is an easy section, a couple of properties that's going to be useful. And sometimes we usually give you at least 2 questions or sometimes 3 questions from this section for your next test. So pay attention. It's not difficult, but it's quite involved. Nice results. So what we're going to do is we talk about finding the inverse of a matrix using different methods so far. But in this chapter, we usually using the determinant. The last thing that I did the other day, if you remember, we proved that if a matrix is going to be invertible, then the determinant of that matrix is not going to be 0, okay? So we are going to use that fact in order to get a nice formula to get to the inverse of a matrix. Okay, this would involve a special matrix that we call it cofactors matrix. And then eventually that will help us to find a new method to solve a system of equation. So try 3 main concepts on this section. So I'm going to summarize it. You had lots of problems in your assignment, in your next practice test. So I will post your next practice test number 1. Okay, and then we go over it. I post a solution for you during the week, so that give you an idea how to prepare for our first test. Okay, 11 questions, 5 questions from the quiz, and 6 questions from the test. Okay, so I will post that practice test by Monday. Let's try to finish this section first. Okay, so what is going to be this section about? First thing to do, we're going to define a new matrix, quite interesting matrix. We call it the adjoint of a matrix. That will help us to get to the method that we are going to be discovered to find the inverse of a matrix and eventually solving the system of the equation. Okay, so what is the adjoint? Okay, this is again a kind of function in future, an operation on a given matrix. But if you are going to take another course in linear algebra, we call it an advanced linear algebra course. Some of you continue something like electrical engineering, or in physics, you need another course in linear algebra, especially if you want to go to the graduate school, getting a master program or PhD. For advanced topics, you need an advanced course in linear algebra. I'll talk about it later for you. And this operation on those cases is going to be very important. We just apply it to a matrix now because it's a finite dimensional. But if you want to go to the infinite dimensional, then you need to replace this one by something more interesting. So that's why we would like you to get to know this. Okay, so you get the name and at least one application for the time being. And in future, if you continue, you will see quite more of these type of ideas. Now, what is going to be adjoint of a matrix? Remember, we are talking about cofactors. Just remind you what is the cofactors. Use the cofactor in order to get to the determinant of matrix. And this matrix would be related to the cofactors. So let's remind you about the cofactors. Okay, so if this is it, if try another one. Okay, if we have a n by n matrix, so if A is an n by n matrix, and remember the cofactors, we denote by Cij. Cij was equal to, it's a -1 to the I plus j. Then from the matrix, we delete the I rows and the j column, and we find the determinant of the resultant one. Remember that determinant of the resultant one was, this is going to be, okay, this is going to be the one. We call it Mij if you like. remember, mij, or just -1 to the I plus j, and that was the determinant of this matrix. Okay, so each cofactor is just a number. It's going to be a number that we use it in order to get our determinant. Okay, and I, as usual. So if A is going to be n by n matrix, and this is going to be is the cofactor. Is the cofactor. Okay, it's going to be cofactor of this entries Aij. Aij, and when or where I is between 1 and n, and j is also between y and n. Okay, so that's going to be the cofactors. Now we are going to introduce a new matrix. Okay, this matrix is going to be called the adjoint metric. So this is it. Now, so this is going to be the case. Now the matrix, the new matrix, the matrix of cofactors. Cofactors. Okay, we put these cofactors as entries of this matrix, the matrix of the cofactors. Okay, cofactors from A. From A is going to be defined by. Okay, is going to be defined by. This is going to be a matrix whose entries are going to be Cij. Okay, so the entries are going to be Cij's, and this. Okay, this is going to be 1. Is defined by the cofactors. Okay, defined by, let's define that matrix. You see, this is going to be 1 Cij. So the first row is going to be C1. Okay, C1, C11, C12, C13, up to the C1n. And then the second row would be C21, C22, C23, etc. to the C2n, and then we continue. That take you to the end row. Okay, the end row, so it's going to be N1, N2, up to the C and N. Okay, so this is going to be the matrix of the cofactor. Okay, now this is going to be a matrix of the cofactor. Now, if you take the transpose of this matrix, the transpose of this matrix is going to be called the adjoint of A. Okay, so the transpose okay, the transpose of the cofactor matrix of the cofactors matrix is going to be called the adjoint. Okay, it's going to be called the adjoint, and that's it. The adjoint. It's going to be called the adjoint of A, and we have a notation for it, and is denoted by, is going to be denoted by, is denoted by adjoints of A. Okay, so what is this matrix? So there you are. So the adjoint metric, you are going to find the cofactor matrix first, then you make a transpose of this one. You know that to make a transpose, you are going to switch the row and the column of that matrix. Okay, so this is going to be the first row. The first column, that's going to be the first row of your, of your adjoint matrix. Okay, so this is it. If you switch it, or you make this one as a column, it doesn't matter, both of them is going to be the same thing. So this is what you are going to have. You are going to have a C11. Okay, so this is going to be a C11, C21, okay, C11, C21, okay, etc. You get to the, okay, you get to the CN1, and then the same thing, you bring this one down. So that's going to be C1, C12, C13, and that take you to the C1, C1N. Okay, it's going to be the first one. And the second one, this is going to be, see, this is going to be C22, C23, C22, C23 to the C2N, C2N, and then you continue to get to the last part, which is going to be CNN. Okay, so we usually find the cofactor matrix first, and then we get the transpose. The transpose gives us the adjoint of a matrix A. Okay, so the row and the columns are going to be just those cofactors that we're going to have. You see, these are the cofactors. Then over here, you switch it. Okay, your job is a matrix would be given to, you should be able to find the adjoint of a matrix for us. Okay, so it's going to be one problem that you're going to have. Okay, so this is it. You form the matrix of the cofactors first. You have to find all the cofactors of the given matrix. Okay, then you put it over here. So you usually go with the 3 by 3, we get the 3 by 3 over there. Then you find the transpose of whatever you got. That transpose is going to be called the adjoint of a matrix A. Okay, so let's get one of them. As example, this is your first job. A matrix would be given, and then you are going to find, okay, this is it, example. We wanted to find the adjoint of a matrix. Okay, this is it. I'd like you to find, okay, find the adjoint of the matrix. It's always possible. You see to be able to find it, and no condition, nothing would be involved. So I give you a 3 by 3 one. So for example, it's going to be -1, 3, 2, and then we have a 0, -2, -2, 1, and then you have a 1, 0, 1, 0, and -2. So this is going to be your matrix. Okay, this is a matrix A, and you want to find the adjoint. You're going to find all the cofactors, okay, and come back and you form your adjoint matrix. This is it. So we are going to find all the cofactors. Just remind the cofactors as Cij is going to be -1 to the I plus a j, then, okay, the determinant of this matrix. So in this case, I and the j are going to be from 1 to 3, okay? So we go for it. We are going to have C11, C12, etc. Okay. So getting the C11, C11 would be -1 to the, okay, it's going to be -1 to the 1 plus 1, which is going to be 2. Okay, and the matrix is going to be A11. So this is going to be what? It's a 1 plus 1. That would be out. And then the matrix A11, you know that the matrix A11 would be what? When you eliminate the first row and the first column. This is it, the first row, first column. So the resultant matrix 0, -2, 1, 0. 0, -2, 1 is 0. You can find it right away. You don't have to write it down to the test. Accepted. You get the determinant. This is going to be 0 minus, okay. This is it. Let's check. So, sorry, eliminate the first row, first column. First row, first column. So the resultant matrix, I made a mistake here. Resultant matrix is a -2, 1. Okay, it's a -2, -2, 1. Okay, -2, 1, and the 0, and a -2. Okay, so -2, 1, -2, 1, -2, 1, 0, -2. So 2 times 2 would be, okay, that's it. So this is -2, -2, so I'll give you 4. Okay, so this is going to be C11. C11 is equal to 4. Okay, then we get the other one. We can do it quickly. This is it. So if we find the C12, C12, this is it, negative 1 plus 2 would be 3, so that give you, okay, for the C12 is going to be negative. The determinant, you eliminate the first row, the second column, so and the matrix is going to be 0, 1, okay, 0, 1, 1, and negative 2. 1, negative 2, the determinant, cross multiply, it's going to be 0, there's a negative 1, there is 1 here, so that give you 1. So C12 is equal to 1. Okay, you eliminate the first row, second column. So 0, 1, 1, negative 2. 0, 1, 1, negative 2. So that would be C12. Okay, so you get the C13. C13, the sign is going to be positive because 1 plus 3 would be 4. So the matrix in question, eliminate the first row and the third column. Okay, so the matrix would be 0, negative 2, 1, 0. 0, negative 2, 1, 0. So the determinant, we cross multiply, that would be 0, negative 2, there is a sign, so that give you 2. So the C13 would be 2. Okay, and then you continue, C21, for example. A C21, the sign would be negative, so eliminate the second row. The second row, first column, 3, 2, 3, 2, 0, negative 2. 3, 2, 0, negative 2. And cross multiply determinant, so that give you negative 6. There is a 6 here, positive 6. And then you continue to get the, okay, and so you can continue to get the others. Okay, so I give you the result. So this is going to be the result. If you get that one, adjoint of A. Okay, adjoint of A is going to be, and this is it. Oh, sorry, first I have to get those common factor first, okay? So let's have the matrix of the cofactor. So this is the matrix, the cofactor matrix, or the matrix of cofactors. Okay, the matrix of the cofactor is just, for C11 is equal to 4, you see. C11 is equal to 4. And then we get the C11, C12 is equal to 1. C13 is equal to 2. And you evaluate the other one, that give you 6, 0, 3, 6, 0, 3, 7, 1, 2. So that would be, okay, I didn't calculate all the others for you here, but they are the same. So this is going to be the matrix of the cofactors. Now you find the transpose of this matrix to get the adjoint, okay? So the adjoint is going to be, this is it. So the adjoint of A is going to be transpose of this matrix. I rewrite it so that you know the definition. It's going to be 4, 1, 2, and this is 6, 0, 3, 7, 1, 2. Okay, transpose of this matrix. And when you get the transpose, you switch the row and the column, and that give you the final answer. So that give you 4, the column, 4, 6, 7, 1, 0, 1, 2, 3, 2. So that give you the adjoint. Okay, so that give you the adjoint of the, okay, of the matrix A. Okay, so not difficult, easy operation, but it takes times. Even the 3 by 3 takes time, because you have to find these 9. Okay, you have to find these 9 entries to put them together. There's no shortcut. You just find them and put them together. Okay, to get the result. Now there are many properties of the adjoints of a matrix, but for the time being, we are very much interested in, okay, the invertibility and the inverse of a matrix. There is one phenomena of these adjoints of a matrix that we are going to be interested in, and I show you here, okay? So look at this one. I give you a remark from this problem. You see in this example, you just, if you multiply the matrix A by its adjoint, that give you something interesting. Okay, note that. in this case, if you multiply the adjoint of the A by A, you see this is the adjoint matrix, adjoint of A. If you multiply this one by a matrix A, and let's see what we are going to get. Okay, so the adjoint is 4. Okay, 4, 6, 7, and this is going to be 1, 0, 1, and this is going to be 2, 3, 2. Okay, this is going to be adjoint. And if you multiply by the matrix A, that gives you a negative 1, 3, and 2. And this is going to be 0, negative 2, 1. And this is going to be 1, 0, and negative 2. If you multiply them together, you see, if you multiply it, what's going to be the result? You see the result would be a 3 by 3 matrix. Check a couple of entries to see what's happened. You see the first row, first column. If you multiply that, give you negative 4. This would be out, and 7. So it's going to be negative 4 plus 7, which is 3. Okay, if you get the second one, if you multiply this one, 4 times 3 would be 12. 6 times negative 2 would be 12. And this would be out. So 12 minus 12 would be 0. So that gives you 0. If you multiply by the third column, 4 times 2 would be 8. And 6 would be 14. But negative 14 would be 0. You see that's going to be the 1. If you try the second one, 1 times 1, negative 1. Okay, negative 1, that would be 0. And then you get a positive 1 here. Negative 1 plus 1 would be 0. Okay, if you multiply the second one, it's going to be 1 times 3 would be 3. This would be 0, and we get 0. So that gives you 3 here. Okay, and you multiply the other one, that gives you 2, 0, and negative 2. So that would be 0, 2. And it's the same for this one. If you multiply it at this row and the column, that gives you negative 2, 0, and the positive 2. So that would be 0. And if you multiply the second one, 2 times 3, 6. Okay, and the negative 6 would be out, and this is 0. Okay, and multiply the third one, 2 times 2, 4, and 3. Okay, this is it. 2 times 2, 4, and that gives you 3, and that gives you negative 4. Okay, so that should give you a 3 again. Okay, so that's going to be 2 times 2, 4, and 3, that give you 7. 7, 4 out, that give you 3 again. You see, that give you this matrix, and quite interesting one. If you factor out the 3, the leftover is an identity. Okay, so this is going to be equal to the 3 times the identity matrix. And this 3, we can show that this 3 is just the determinant of a matrix A. You see this number over here. Easily, we can find easily the determinant of the A, and we are going to do it later on. So that give you the determinant of the A, times I, which is quite interesting, because the determinant is just a number. Okay, this determinant is a number. If this number is going to be a non-zero number, okay, if it's going to be non-zero number, you know that the A is invertible. And if it's going to be non-zero number, we can divide both sides by this number. If you divide both sides by this number, the other part would be I. Okay, so this means these two are going to be invertible. So this basically means if you want to find the inverse of the A, inverse of the A would be what? Inverse of the A would be just the adjoint matrix, but divided by the determinant. Okay, so that's property. If you write it down in AIJ form, you will get the same thing. It's going to be a little bit messy, but eventually we get it. To get these results, these zeros would appear quickly. Okay, and so you can check it with the 3 by 3 in general, but you see this conclusion is quite interesting for us. And this is the one we are going to use for the adjoint of the inverse of a matrix. So this basically means the inverse of A. Remember, we did have the conversion method. And you must know it on the test, we may ask to find the inverse of a matrix. by inversion method, and we ask you to find the inverse of a matrix by adjoint method. So one problem probably would be given to it's 2 parts or 2 problems. So in this case, you see the adjoint of the A is simply is going to be what? Is going to be a quotient. You see 1. This is a number, determinant of the A, 1/2, 1/3. In this case, the 1/3. Okay, this is going to be the case times the adjoint of, okay, the adjoint of A. Okay, so for this problem, easily we can find the inverse of a matrix, and we are going to do it officially in a minute. Okay, this observation will tell you that why we are interested in the adjoint of a matrix for the time being. So that gives us a theorem, if you like. Okay, I just want you to see it, because I usually, when it's a face-to-face, I try to prove it, to give you the proof, but you can check the proof, yourself if you like, but the main idea is this one that I gave you. So that gives us this theorem. This is your job. This is the problem that I talk about it. We give you one in your next test. We give you a matrix and we ask you to find the inverse using its adjoint. So I remind you that this theorem would give you what? The inverse of a matrix, the inverse of a matrix, not by inversion method, by, okay, given by its adjoint. Okay, we call it adjoint method. The other one is inversion method. For the other one, you have to know that you just do the elementary or row operation of a matrix, you change it to the identity. That was the other one. But this one, it takes a little bit more time, but it's nice. Some people like it. So in general, if we don't say any method, you are free. You can use either method you like. And that's more exciting, okay? So this is a theorem, exactly the one that I show you. If A is going to be, if A is an, okay, if A is an n by n matrix, okay, n by n matrix, okay, n by n matrix, it must be invertible with determinant of A not equal to the 0. So this basically means A is invertible. A is invertible. Automatically you will see it because you are going to find the determinant to get this one. Okay, if this is going to be the case, then of course we have an inverse. So what's going to be the A inverse? A inverse is going to be equal to 1 over the determinant of the, remember this is a number, times the adjoint of A. Okay, this is the one. Okay, so this is the case, and that property that I gave you is quite useful. You have 3 proofs in your book. I put all of them in your next practice one that related to this formula. Okay, you can use it anytime you like. The way I did it, I just remind you again, and this is going to be the proof. You have to know this identity for those 3 problems in your book. We are not going to ask you to prove this one, but we are going to ask you to prove one of those 3 problems that we put it into the, okay, into the next practice one. So the proof is going to be this one only. Say note that. Note that. This is the one that you memorize it and use it anytime you like. A matrix A times its adjoint. Okay, this result is always determinant of the A as a number times identity matrix. You can use this one anytime you like. And you need it for all those 3 proofs that one of them would be given to you on the test, and I will review it for you later. Okay, there you are. So as I did it for the other one, if you multiply the adjoint of a matrix by itself, that gives you almost identity. Now the determinant of A is not equal to 0, so we can divide, and this will tell you that what? This will tell you simply that So this means, remember, if the product of two metrics is going to be identity, one of them is the inverse of the other one. So this is just a number, 2i, 3i, 4i. So this means the A is invertible, and the A inverse, okay, A inverse is like dividing, if you like. So the A inverse is going to be, if you divide this one by the determinant of the A, so that gives you 1 over that of A, determinant of the A times, okay, times it by adjoint of a matrix A. Okay, so that gives you the formula that we're going to be interested in. Okay, so what we did, we divide both sides by determinant of A first to make this one to be I. So the inverse would be adjoint of A divided by determinant of the A, divided by a number. Divided by a number, we usually write it down in this format. Okay, so make sure to memorize it. And two problems would be given on the test related to this formula, very popular. And the first one is, I do this one because we already done everything on it. We give you a matrix and we ask you to find the inverse. And this is the way we give you instruction, use the adjoint. This means no other method. Okay, use the adjoint of A to find, okay, to find A inverse where I just use the same matrix to save time, but we get more when we get to the review. It's going to be A, so -1, 3, 2. That's the same matrix that I use, -2, 1, okay, -2, 1, and this is going to be 1, 0. Okay, that's going to be 1, 0, -2. Okay, so that gives you 1, 0, -2 over here. Okay, so your job is you have to find it takes a little bit more time. You have to find the cofactor matrix. Remember, cofactor matrix, then we get transpose of the cofactor. Transpose of the cofactor give us the inverse. We have to find determinant. You see, my suggestion is first check the determinant, because you must make sure that this matrix is invertible. Okay, if it's not invertible, you're done. Okay, make sure check the determinant first for these problems. Anytime they say use the adjoint, you need to make sure that it is invertible. So make sure that sometimes the determinant of the matrix is 0, so it's not possible, and don't waste your time. So first thing to do, check the determinant first. Okay, check the determinant of A not 0 first. Okay, it's not a big deal. We can just find the determinant just using the usual method. So the determinant of the A is equal to, it's expanded first row, second row, doesn't matter. Just go with the first row. And this is it. It's going to be -1. Eliminate the first row, first column. This is the matrix. -2 times -2 will be 4. Okay, it's going to be 4 minus 0. Done. I go to the next one. Okay, this is it. Okay, or this column, it doesn't matter. Okay, you can go with the column if you like, or the row. If you go with the column, it's easier because this is 0. So we go to this part over here. So it would be a +1. Okay, a +1. You eliminate this column and the row. So 3 times 1 is going to be 3 minus -4, which is going to be a +4. Okay, so the result is going to be a -4 plus 7. So the determinant is going to be 3, is not 0, so we are safe. Okay, so it's going to be the determinant of a matrix. Okay, so what I did, you can use any row of the column, second row, first column, they give you the same number. The one that I use the first column to distribute it. So I use the -1, first row, first column, -1. So I get this matrix. Then I don't need the 0, so I go to this one. This is on, okay, it's going to be on the third row, first column. So -1 to the, okay, -1 to the fourth would be positive. Eliminate the row and the column, just get this matrix. 3 times 1, 3 minus -4, which is the positive 4. Okay, so we get the fact that A is invertible. A is invertible. A is invertible, and then you are going to find the adjoint. We did it, but you have to find it yourself. Okay, so you find the matrix of the cofactors, and then you get the matrix of the adjoint. We have it from the previous example, so we use it. Okay, so there you are. You have to find, if you like, find the adjoint matrix, the adjoint matrix of A. We have it from the previous example, so I just use it. So this is going to be the okay, it's going to be the adjoint matrix that we did it previously. And we got this one, it was 4, 6, 7, 4, 6, 7, 1, 0, 1, and then 2, 3, okay, 2, 3, 2. So this is going to be the adjoint matrix, okay? Now we know that our A inverse is going to be, you see your A inverse is going to be a quotient, a portion is going to be 1 over that of A. Okay, this is the formula. Determinant of the A times, okay, times the adjoint matrix. Adjoint matrix. Okay, so this is going to be the case. It's going to be equal to, you're going to multiply this one by 1/3. Okay, the determinant is going to be 3. So just divide each increase by 3. So your inverse is going to be, this is it, that give you a 4/3. Okay, 4/3. A 6/3 would be 2. Then that give you 7/3. Okay, over here, that give you 1/3. Okay, 1/3, 0, 1/3. And the last one is going to be 2/3, 1, and the 2/3. So that give you the inverse of your matrix. Okay, 4/3, 4/3, 2, 7/3, 1/3, 0, 1/3, and the 2/3, 1, and 2/3 is going to be your A inverse. And this is it. Quite interesting method. And the way you can manipulate in this identity is quite interesting. And you will see it. You see your next proof is going to be this one. It's 3 problems, and I will do it with the review to help you. Okay, so that's the first question of this section, the main question. Easy. A matrix would be given. You would like to find the A inverse. Okay, but remember, A inverse using the adjoint format. So you have to use this method. So if you say inversion method, you have to use the inversion method. If you don't say anything, you are free. You can use any one you like, okay, to get this number. Okay, so quickly, we want to know how it's going to be the application of this one. Okay, now there are the application, when you put these adjoints together, give us a very interesting and easy method to solve a system of the equation. And this method was proved by a British mathematician. His name is Cramer. So that's why this method is going to be called Cramer rules. Okay, so Cramer rules is going to be the rules that use the adjoints format, resulted in very easy formula that you memorize it, and you can solve the system by the Cramer rules. So we give you one question. That's the second question that I talk about. Okay, so let's get that one done. So a system of the equation would be given to remember. If you say using Gaussian method or elimination method. Elimination method means that you work on the augmented matrix, you change it to the row echelon form or echelon form or reduced echelon form, and you solve your system. Okay, but this method is Cramer rules. Cramer rules would use the notion of the determinant. So what is going to be this rule? Interesting rules. Okay, there you are. What is Cramer? Okay, Cramer rules. for solving that method. It's kind of just elimination method, but when you put them together, you can connect it to the determinant of a matrix. Okay, I give you the theorem and then I explain it. Okay, so we have a system of an equation in variable and we want to solve it. Okay, there you are. If a system, okay, if a system of n linear, okay, and linear equations in n variables, okay, it must be, you know, the matrix of a coefficient must be a square for this method. Okay, has a has a coefficient matrix, coefficient matrix A. So A is going to be coefficient matrix of a system, okay, such that the determinant of the A is not going to be equal to the 0. I'm going to tell you later what will happen if it is 0. Okay, the one in your book, your old determinant not 0, but we are going to argue that one for you. Okay, such a determinant of A is not 0, then the solutions. Then what's going to be the solution? Okay, then the solution of the system, solution of the solution of the system is, okay, in order to find the first variable, x1 is equal to the ratio of two numbers. The top numbers on the top, we call it determinant of, okay, this is it, we call it determinant of A1. I'm going to explain it. And the bottom one, we call it determinant of, okay, the determinant of the A. Determinant of the A, you already find it, okay? This is going to be your determinant of your matrix. Now, what is going to be A1? You see, for the A1 is going to be, you check to see, this is X1. This is going to be the X1. So what we are going to do, you are going to, in order to get the A1, you are going to eliminate the first row and the first column of a matrix A. So if A is going to be a 3 by 3 matrix, you delete the first row and the first column, that matrix would be A1. Then you are going to find that determinant of the, okay, determinant of the A1. But the system is going to be, okay, something is missing over here. Let me finish it, I'll explain it. I missed something. Okay, is this X1, what is going to be the X2? With this format of the theorem, there is another definition of these AIs. I'm going to explain it. Let's write it down, all of them. Okay, we get the Xi. Xn is going to be what? It's going to be determinant of the A over determinant of the AN. Okay, so let me tell you what is going to be this. You see, we got this matrix A. Then we get the determinant of the A. Then we want to find the X1. You see, this system of the equation, you know that the system of the equation would have some constant term, constant numbers. You see, you get 2x plus 5y equal to the 7. So as we did it before, the system is of the form of ax equal to the b. The system is going to be ax equal to the b, and the b is going to be the constant term. The one that I talked about, it was good for you know, homogeneous system, ax equal to the 0. But what we are going to do is, you see, you find the determinant of the A. If you want to find the x1, you go to the A, you replace the first column by that constant vectors b. Okay, those constant numbers that we have. So A1 again is going to be an n by n matrix, but the first column of the A1 is not going to be the coefficient of the x1. They are going to be those constant vectors. If you go to the A2, you want to find the x2, you go to the matrix A, you replace that column, the second column, by constant B. You get the A1, okay? So in general, the top matrix is, let me just explain the top. Okay, this is going to be where. Okay, this is it. Where the ith column, the first, the second. Okay, this is it, where the ith column. Okay, the ith column of the matrix. The matrix AI, okay, is going to be going to be the column. Okay, that's it. It's going to be the column vector, if you like, column vector of constants in the system. Okay, and the constant B, if you like, in the system of the equation, system of equations AX equal to the B. Okay, so you replace, you want to find the x1, so the first column are coefficient of x1. Replace it by the B. If you want to find the x2, okay, x2, you replace the second column by the B to find the determinant of the A2, A3, AN. Okay, that give you the result. Okay, very easy formula and very easy to prove. Let me give a proof of how we're going to prove it. Okay, you see the role of the adjoints that we talk about it. Let's see. You see, this is it. Consider this system. Okay, so consider the matrix equation. Matrix equation of the system. Okay, the matrix equation is what? Is AX equal to the B. Okay, X equal to the B. And you know that this is going to be what will happen then. Then, as we talk about it, A is invertible. A is invertible. And what we have now, you see this is AX equal to the B. So your X would be what? Your X would be A inverse times B. So you have to find the inverse. But what is the inverse? You see what inverse is, but okay, A inverse, remember the A inverse is what? Is 1 over the determinant of the A times the adjoint matrix, adjoints of A. So if you substitute, so the matrix X would be, the matrix X is going to be, we can substitute here, so that you 1 over the determinant of the A. The determinant of the A is going to be just adjoint matrix of A times the constant matrix B. Okay, the constant matrix B. Okay, now remember the adjoint matrix. The adjoint matrix is transpose of a, okay, it's a transpose of a cofactor matrix. And the B is just a column matrix. So in order to get the X is what? X is n by 1, okay, matrix, if you like. So suppose you want to find, so in this case, therefore, if you like, if you want to find the I term of that column vector, so it's going to be the I form of this one. This is going to be 1 over the determinant of the A. Okay, then you have to find the, okay, you have to multiply these two together that we're going to have. Remember, this is what? This is that n by n matrix, and this is just n by 1. So we get the same one. But if you want to, okay, so it's going to be 1 over that of A. If you multiply these together, okay, the conclusion is going to be this one. Okay, so you have to multiply the, so it's a kind of, just show you the result. You see, this is going to be your B, which is going to be B1, B2, up to the Bn. Okay, so what you do is you pick the I column of I row of the adjoint matrix, then you multiply by this column. If you multiply them together, that give you the result. It's going to be B1, B1, okay, CI1 plus B2, okay, CI2. Then you continue to get the Bn, okay, Bn, CIN. Okay, that is going to be the result. And this is exactly, you see, there's going to be xi is equal to, this is 1 over the determinant of the A. This is exactly is going to be the determinant of that matrix that we talk about it. And this is going to be the determinant of the matrix, okay, the matrix AI. So this would be like the, you see, usually these are going to be cofactors, and these coefficients are going to be what? It's going to be entries of a matrix A. Entries of the matrix A, A11, A12, A13, etc. In this case, you replace those entries by the entries from the constant vector, which is going to be B1, B2, B3. So that gives you exactly the matrix AI. What is the matrix AI? Is the matrix A in which you replace the column I by the column of a constant vector. Okay, so in general, that's exactly what we talk about it. So this means if you want to find the xi, you simply divide the determinant of the matrix AI divided by the determinant of the A. Okay, so if you like to see the proof, this is the proof. Okay, so that would show you that definition of the adjoints that we talk about it. Okay, so basically we start with the AX times B, X would be A inverse B. So we replace the A inverse by the adjoint over that of A. So we multiply these two together for the 3 by 3, 2 by 2. If you just consider one entries of this matrix, the I term, if you like, so this is what you are going to do. You are going to multiply the I terms of the first one by these column vectors that you're going to have. So the I terms of the adjoint matrix is going to be CI1, CI2 up to the CIN. When you multiply it, that's exactly the determinant of a matrix resulted by replacing the I column of the A by the constant matrix. Okay, so if you like to see the method, the proof, but the action that you are going to do for us is easy. Okay, I just wanted to see the application. The reason that we introduced that system was just to get to this one. Okay, application is easy. We give you one problem. We don't give you the proof. We don't ask you to prove it for us. Okay, you just use the formula and get the result for us. So example is going to be, okay, example is, they give you the instruction, use the Cramer. Okay, use the Cramer rules. Use Cramer rule to, okay, to solve the system. Okay, to solve the system, and easy system would be given to you, then you are going to use this one to find it. Okay, so this is it. You are going to find determinant of 4 matrices for us, then that's done. Okay, so what's the system? This is the system. Negative x plus 2y minus 3z equal to 1. And in this case, we have a 2x plus z equal to the 0. 3x minus 4y plus 4z equal to 2 to get this one, okay? To get that system done. There you are. First thing to do, as usual, you are to find the okay, that is going to be the system that we are going to have. Okay. So we find the matrix of the coefficient that we have. Okay, so this is it. Note that. This is the matrix of a coefficient. So -1. Okay, -1, 2, -3. And that's going to be 2, 0, 1. It's going to be 3, -4, 4. This is going to be the matrix A. And the matrix of a coefficient is going to be 1, 0, and 2. Okay, so that gives you the matrix of the coefficients. So we check the determinant of the A first. Okay, easy to find. Just use the usual method to find the determinant of a matrix A. So what's going to be the det of A? Okay, usual method will do it for you. Nothing to worry about. Just extend it from the first row. It's going to be a -1. Eliminate the first row, first column. That give you 0. Okay, it's going to be 4. And I go with this one. It's going to be -2 times the first row, second column. So that give you 8 minus 3. Okay, and that's going to be plus a -3 times. So that give you a -8. Okay, we put them together. So that give you -4. And this is 5, -10. Okay, that give you a -10 plus 24. Okay, the result's going to be 10. So the determinant of A is equal to 10. So it's a non-zero, and we keep going. Okay, just make sure this is a non-zero number. I will tell you what you are going to do when it is going to be 0, but in the one in your book, you always get the non-zero one. Okay, so that's the first part. Now you want to find the x1, the x, and the first one, this is going to be x. If you want to find the x, so you need to find the determinant of a matrix, we call it A1, divided by the determinant of A. Now what is going to be A1? You see, for the A1 is the first column, is the column of the x. So we replace the column by this constant matrix. Okay, so this is going to be 1, 0, 2. Okay, 1, 0, 2, and everything else would stay the same. So that gives you 2, -3, and that's going to be 0, 1, -4, 4. Okay, so this is how we're going to form those matrices. Since x, the first column is going to be coefficient of the x, so we replace the first column by the b. So find the determinant of the A1. Okay, so this is the baby to it. So this is it. We get the 1, 2, -3, 0, 0. So we can distribute it in this second one easily to find the determinant of the A1. So the determinant of the A1 is going to be equal to, use this row. This would be 0, 0. So the entry was 1 times, eliminate the second row and the third column. Okay. So the resultant matrix is going to be 1 times -4 would be -4, and the minus -4 here. Okay, so this is the case, but we check this sign to make sure you know this is a second. Okay, that was second and the third. Okay, so 2 and 3 would be 5, so that give you a negative one here. Okay, there is going to be a negative one here, so it's a negative because of the sign. Okay, there you are. We get the second and the third. Remember, -1 to the second and the third, which is going to be -1. So the result would be 8. So the determinant of the A1, determinant of the A1 is going to be equal to the 8, and we are ready to give the x. So x is going to be equal to determinant of the A1, which is 8, divided by the determinant of the A, which is 10. You simplify it, that give you 4/5. Okay, so that's x equal to 4/5. Okay, not difficult. And be patient to get these numbers done nicely. So that's the x. We want to find the y. So we continue. Y is equal to the determinant of the A2. Okay, over determinant of the A. So we have to form what is the matrix A2. So for the A2, what you are going to do is you have to replace, okay, it's going to be matrix A2. The first column is going to be unchanged. So that gives you a -1, 2, and 3. The second column, you're going to switch it into the B again. So that would be 1, 0, 2. And the third column is going to be unchanged. So that gives you a -3. Okay, -3, 1, and 4. So this is going to be a matrix A2. Okay, now we find the determinant of the A2 to get this one. Okay, so find the determinant of the A2 just using ordinary method, whatever determinant of the A2. Not a big deal, picking each of these to get these numbers. Okay, I just go with the first one, ordinary one. It's a -1, you eliminate. So that gives you 0 minus 2, the first one. I get to the next one, it's going to be -1 times, eliminate. Okay, that gives you 4. I'm sorry, the first one was, this is the first one, 0 minus 2. So I do the second one. So I have 2, 4, which is 8 minus 3. Then I get the -3, the first row. So that gave me 4. Okay. So we simplify it, that give us a 2. And this is going to be -5. And this would be -12. Okay, we put them together. In this case, that gives us a -3, -15. -15. So we are ready to give you the y. So y is going to be equal to the -15 over the determinant of the a, which is 10. So you simplify by 5. So that gives you 3/2. Okay, so y equal to the -3/2 is going to be the second, okay, y. Okay, that's for the y, and we continue with the z. So what is going to be the z? In order to get the z, we have to find the determinant of the A3. That's of A3 over the determinant of the A. Okay, so what is your matrix? The matrix is going to be A3. For the A3, we have to replace the third column, the Z column, okay? So the first 2 columns would be unchanged, the -1, 2, 3. And the second one would be 2, 0, -4. Okay, now we switch the third column by B, which is going to be 1, 0, and 2. So this is going to be A3. Okay, we find the determinant of A3, which is easy because the second row is lots of zeros. So determinant of A3, the depth of A3 just using the second row, just give you two times, eliminate, okay, the first column, the second row. So that give you 2 times 2, 4 plus 2. Okay, 4 plus 2, that give you 6, 8. Okay, so I get to this one, I get to this one again. And what is this? This is going to be the second row and the third column. I missed a sign again. Okay, this is a -2 here. Okay, this is going to be a -2 because the first and the second and the first. So when we eliminate it, okay, eliminate this, so that give you, that's it, 0 times 2 would be 0, and this is going to be 0. It must be something wrong. And that's a 3, -4, 2, 2, 0, 0, and -1, 2, 1. And this is what I did. Just check it again. Okay, this is the one that we eliminate. The second row and the third row we kill. Yeah, I mean, my original one is correct, sorry. That's going to be 4 plus, this is 4 plus, this is it, 4 plus 4. 4 plus 4, I get the -16. Sorry about that. Lots of numbers. So that of A3, that of A3 would be -16. -16, so the Z is going to be equal to, I put the Z here. So we have everything in one setting. So the Z is going to be -16. Okay, it's going to be -16 divided by the determinant of the A, which was 10. So you simplify by 2, the final answer would be 8/5. So the final answer, what is your, okay, and the final answer, X is 4/5. Okay, X is 4/5, Y is -3/2, and the -8/5. Just double check it because I just did it live. I don't know, but I think that's correct. Okay, so not difficult, but be patient to get this through. Okay, be patient to get this through. And the one in your book, all of them are going to be, you see, this method can be used when the determinant of A is not equal to the 0. In that case, you get one solution, unique solution. But you know that a system of the equation can have infinitely many solutions, or the system of the equation can have non-solution, 0 solution. So what would happen that we will get those? I'm going to give you a hint. You see, the hint is going to be if the determinant of the A happen to be 0. If this determinant happen to be 0, this means you cannot use this formula. You see, in this formula, you are not going to get any solution. But you are not going to have a unique solution. So when you don't have a unique solution, there are 2 other possibilities. Which one is it? Is it infinitely many solution, or is just, okay, if it is inconsistent? So what you have to do, you have to continue. You have to continue getting these, okay, determinant of the A1 and the A2 and the A3. If the determinant of the A is 0, and one of these on the top happen to be a non-zero number, like 2, 5. So for one of them, you get 5 divided by 0. You know that 5 divided by 0 is undefined. So in that case, the system has no solution. Okay, so if at least one of these DAIs, those resulted matrices, would have a non-zero determinant, the system is going to be inconsistent and you get no solution. But if you get the case that all of them are 0, if you get all of them 0, the situation would be what? Would be 0, 0, 0, 0, 0, 0. Okay, a kind of indeterminate form. If you get to that one, the conclusion is the system would have infinitely many solutions. Okay, so you have it, you don't have it. I don't see it in your book, but you may get it on the test. So I give you a hint. Just make sure that don't be surprised if you see this. Okay, so this remark would be useful. The other thing is sometimes we may want to just to check the method to see if you know it. So we may give you a system of the equation, but we may ask you only for value of one of these unknown, okay? So if on the test we ask for the z only, if we ask for the z only, you don't have to do all of them. You do only the part that gives us the z. Okay, so be careful. So if we ask you to solve the system, you go through it and we get it. Sometimes we just want to test to see if you know the method. So we may ask you only find the y. So what you do is you have to go to the first step. You have to find the determinant of the a. Then you check one of these determinants because these are all algebra. And sometimes we just check one of them. Okay. So be careful, don't do too much if you like, if it's going to be on the test. And this remark. So remark regarding the Cramer rules. So the first part is going to be note that for the previous theorem. Note that the following okay, the following possibilities when one uses Cramer's rule. Okay, can happen if you like. Okay, so what is the first one? The first one is that if the determinant of A is not zero, then the system, then that system that you have, the system AX equal to the B, if you like, has a unique solution, has a unique or one solution, unique solution. That's case one. This is the one that is happening most of the time, okay? So the second one is the case that if the determinant of A is equal to the zero and determinant of AI is also equal to the zero for at least one I, if you like, at least one value of I. Okay, you know that when I is between 1 and n. If at least one of them is going to be, sorry, at least one of them to be, let's take this one, not zero. For at least one value of I, not zero, then if this is going to be, you get something like 5 over 0, then the system, okay, the system has no solution. Has no solution. So this means if you get the determinant of the A equal to 0, you have to continue. As soon as you get one of those non-zero, you stop. The system has no solution. And the third one, this is where all of them would be 0. If the determinant of A is equal to 0 and the determinant of AI is equal to 0 this time for all values of I where I is between 1 and n. If this is going to be the situation, then okay, then what we have is that then this is it. The system has infinity many solutions. Then the system has infinity many solutions. Okay, you will see one of them in your next practice test. So if that situation happens, don't be surprised. You continue. Don't just say no solution. Some people, as soon as they get data of A equal to 0, They don't continue. They say there is no solution. No. You have to check you just to continue to see which one is it. Is it the case that you are not going to have no solution? Or this is going to be the case that you are going to have infinitely many solutions. Okay, so you have to continue to get those numbers. So be careful when you use the Cramer rules. So, you may see it. You may see it when you go through those problems. You put it in your practice one so they can see it. Okay, this is going to be one problem, one application. There is one more application. You may have seen this one in algebra. Sometimes we talk about it when we teach college algebra, but you may not have seen the proof of this fact. We can use the determinant in order to find the area of a given triangle, okay? So I give you a proof. This is one of the problems in your book. They ask you to prove it. So I give you the proof. We are not going to ask you the proof, but the conclusion is important because there are 3 more problems that you have to use this one to solve those problems. So it's like, giving you the solution of those problems, but you have to know it, okay? So that was the first remark. The other remark is going to be, okay, the other remark is going to be the determinant of a matrix, the determinant of a matrix can be applied to find the area of a given triangle. Okay, and there is another conclusion that you can get from here. So it's nice to see it. It's quick to prove so that you don't have to prove it, it's in your assignment, but you have to know the conclusion. Okay, so what is going to be the conclusion? So we write it down as a theorem. So this means you can use it when it's a theorem. Okay, it's a theorem, and that theorem will give you area of a triangle. Of course, using linear algebra, using the idea of a determinant. Okay, so this is it. The result is going to be the area. Okay, the area of a triangle. The area of a triangle with vertices. Okay, with vertices x1 comma y1, x2 comma y2, and x3 comma y3 is given by nice formula. The area is going to be equal to positive negative 1/2. This positive negative is to guarantee that this result is positive. So if you have a positive result, you just call it 1/2. If you have a negative one, you have to call it negative so that negative would be positive. So it's going to be positive negative 1/2, determinant of this matrix. Okay, determinant of this matrix. And the matrix are going to be, this is it. You get the x1, y1, 1, x2, y2, 1, x3, y3, 1. You have to memorize this matrix in order to solve that 3 problems in your book. Okay, so that would be the formula. So we find the determinant of this matrix first. If the determinant is positive, so we just use positive 1/2 times. If this determinant is negative, use a negative 1/2, so that to guarantee that the result is always positive. Okay, so I just show you a short proof. Just, although we don't need the proof, but I just wanted to see it. Okay, just how we construct and how we relate it to the, It's a famous formula in algebra, and there are many other proofs of this fact. Okay, but just to give you an idea, just pick 3 points on the xy plane. Okay, this is it. Pick 3 points. Suppose this is one of them. Okay, and pick another one here and another one here. Form a triangle. This is going to be your triangle. Okay, so we are going to call the point. Okay, this is the first one, second, third one. So I'm going to call this point, okay, call this one x1, y1. So this is x1, y1. This one, I'm going to call it x2, y2. This top one, I'm going to call it x3 and the y3. Okay, and we want to find the area of this triangle. What we are going to do is we are going to divide in different parts. You see, this point, this is going to be, so this is going to be x and the y. Okay, this is x and the y, x1 and the y1. So this is going to be x1 and this is going to be y1. Okay, for this one over here, this is going to be x2. Okay, this is going to be x2 and this is going to be, okay, y2. And this last one, this is going to be the top. Okay, this is going to be x3 and this is going to be y3. Okay, this is a situation we're going to have. Now, what we are going to do is going to be, we just, we are going to have 3 trapezoid, if you like. This is one of them, you see. This is going to be one of them, the bottom one, outside one, outside one. Then I have one inside here. You see, one of them is here. And the other one is going to be here. Okay, so in order to find the area of a, in order to find the area of a triangle, this is the area of a triangle that I'm interested in. So what I'm going to do is I'm going to add the area of these two one. You see the first one and the second one. Then I subtract this third one, if you like. Okay, so I'm going to have 3 trapezoid, if you like. This is, one of them is this part, I call it T1, and this is going to be T2. Okay, and this bottom one is going to be T3. Okay, so the area, if you like, the area of a triangle, is going to be equal to, the area of a, these are just stand for the area of a T1 plus the area of a T2, okay, minus the area of a T3. Okay, this is T1, you see trapezoid T1. This is T2. Then I subtract the bottom one, so that give me the area that we are, you see, this is the triangle. Okay, and you know that the area of a trapezoid is going to be the product of what? Okay, you add the 2 sides and multiply by its height, if you like. I do one of them so that you see it. So the area of these trapezoids are going to be, you see, this is going to be the area of trapezoid. One, if you like, T1. So for each triangle, you know that it's going to be 1/2 of the base, the sum of the bases, times the height. This is what would happen. Okay, so what I do for the T1 is going to be equal to, okay, the T1, the height are going to be, for the T1, the height are going to be the y coordinate. y1 and the y3. Okay, so this is it. Sorry, the bases y1 and the y3, and the height is going to be x3 minus x1. Okay, it's going to be 1/2, 1/2, 1/2 y1 plus, you see, y1 plus y3, and the height are going to be different. You see, x3 minus x2, x3 minus x2. That's it. And similarly, we got the other ones. You see, for the T2, this is the T2. You get the, okay, we get the y2 and the y3. So it's going to be 1/2. Okay, y2 plus y3. And this is going to be difference of the x's, x2 minus x3. And the D3 would be 1/2. It's the bottom one. The y-axis is going to be y1 and y2. y1 and y2. And this is going to be x2 minus x1. That's it. Okay. If you put them together, you get the formula. I'll just give you the idea. So, you know, that's a very classic result. It's eventually, they call it the Heron formula, but this proof is just an excuse for the, okay, for the linear algebra. So if you add them together, it's a T1, T2, T3. You need a little bit of factoring algebra to put them together really. And if you do all those multiplication and take out the half, so if you want, it's going to be x1, y2, x2, y3, okay, x3, y1, and the x1, y3, and the x2, y1, and the minus x3, and that's going to be y2. Eventually, it's going to be the determinant that we talk about it. Okay, it's the 1/2 of the determinant of the x1, y1, 1, x2, y2, 1, x3, y3, 1, and you're done. Okay, just for your information and help you to solve this is a problem in an exercise in that section 2.3. Maybe I have assigned it, I don't know. But we just wanted to explain the result, but you can use this result anytime you like. There are two conclusions that we're going to be interested in. Okay, the conclusion is going to be, sometimes they give you 3 points and they ask you if these points are collinear. Collinear means if they are going to be on the same line. So if the points are not going to be on the same line, they will form a triangle and they will have an area. So if you find this determinant and it's happened to be 0, means the area is 0. So the points are going to be collinear. Okay, so that would be nice. Let's just give you an example of this one and those conclusions, and then we are done with all the problems and the idea of this section. So it's an important section regarding the test. Just make sure you give these examples, review it. So you can use that formula anytime you like, for example, to solve this problem. Find the area. Okay, find the area of the triangle. Area of a triangle whose vertex is given to you. Okay, whose vertex or vertices are 1, 0, 1, 0, 2, 2, and 4 and 3. See, that's how we are going to give you the problem. It's a 3 cases and we put all the 3 in one problem. Okay, so there you are, solution. And label this point, form that, okay, form that matrix to get it, okay. Substitute the numbers. So that's it. Label this as x1, y1, x2, y2, x3, y3. Okay, so this is it. A is equal to the positive negative 1/2, the determinant of this matrix. X1, Y1, okay? So it's a X1, Y1, 1, X2, Y2, 1, X3, Y3, 1. So it's going to be positive negative half. Just bring these numbers. 1, 0, 1, 2, 2, 1, 4, 3, 1. That's it. Find the determinant, just use the first row if you like. It's going to be positive negative half. The determinant, I go with the 1, eliminate the first row, first column is going to be 2 minus 3. The next one is 0, so we get a 1. Eliminate the first row and the last column, 6 minus 8. Okay, it's going to be positive negative half. And the inside is a negative 1. And this is going to be negative 2. So it's going to be positive negative half times a negative 3. So we use a negative to make sure that the result is a positive number, okay? This is where you pick which. So we pick only negative 1/2 times a negative 3. So that gives us a 3/2. So the area is going to be 3/2. Whichever unit it's going to be a squared. Okay, not a big deal, but you have to know it. Okay. So just give you the hint for the other application that we talk about it. Okay. And that solved the other two problems that we have. 3 points are going to be collinear if they don't form a triangle. So 3 points, x1, comma y1, x2, comma y2, and x3, comma y3 are collinear, means they lie on the same line. Collinear. Collinear if this determinant is 0. They don't form a triangle, so that area part must be 0. x1, y1, 1, x2, y2, 1, and the x3, y3, 1, b 0. Okay, and can be easily checked. That's one. The other two is the other one. The next one is a bonus. You know that if 2 points are given to you, you can write the equation of the line. You can write the equation of the line using the slope. But we can use this idea to find the equation of the line. You see, if I give you 2 points, this is x1, y1. And this is going to be x2, y2. If you are interested in finding this equation of the line, you know that we can find this slope. But the other thing that you can do, you see, pick another point here, call it x, comma y. 1, 2, 3. You see, they are collinear because they are on the same line. If they are collinear, this matrix must be 0. So you are going to pick x1, y1, x2, y2, 1, x, y1. You let it equal to 0, that gives you the equation of the line. Okay, this is idea of using the determinant. So not bad to know this one too. So this is it, an equation. In one problem in your book, and we may ask you an equation. Okay, an equation of a line or of the line passing passing through the points, x1, comma y1, x2, comma y2, and x3, comma y3 is given by, okay, given by that determinant. I just put it here because I don't want to keep it here. Okay, this is it. Determinant R x1. Sorry, why I write 3.1. Sorry about that. I need only 2 points. The third one is the one that we are going to, you see, 2 points would be given. An equation of the line passing through the points x1, y1, x2, y2. You know that. You can find the slope and write the equation of the line, but don't do it on the test. We need these ideas. Okay, so we put it here. We pick the third one ourselves. x1 with this color. x1, y1, 1, x2, y2, 1. And you pick another one yourself. You let it equal to the 0. That gives an equation in terms of x and the y, and you're done. Okay, quickly one example. So the area problem, collinear and the equation together, it's just one concept and that you have to know it. Okay, so I'll give you one example quickly to make sure that you know what you are going to do for us in case. So this example, okay, so 3 points would be given and you've been asked to check if they are collinear. Okay, that is going to be the one. We want to determine. Okay, determine if the points are whether the point. Okay, determine whether the point are going to be whether the points are collinear. Means they are going to be on a straight line. When they are on a straight line, there is no triangle. So just check the area problem. Okay, so the points, we check this. -1, 0. Okay, 1, 1. And the 3, 3. Okay, check the area formula if you like. So you label your points x1, y1, x2, y2, x3, y3. Okay, you check this one. x1, y1, 1, x2, y2, 1, x3, y3, 1. Substitute, simplify. It's a -1, 0, 1, 1, 1, 1, 3, 3, 1. Find this determinant. If it is 0, the answer is yes. If it's not, the answer is no. Okay, there you are. I'm going to distribute along the first one is a -1 times. Eliminate the first row and the first column. That give me 1 minus 3. I don't have the second one. I go to the third one. So it's going to be +1. Eliminate the first row and the column. That give me 1, 3. Minus 1, 3. Okay. Check the first one again. So that's a -1. So that was the case. There is nothing here. So we check the last one. That's it. So that gives us the 0, but this is going to be -2, +2, not 0. So the answer is no. They are not collinear because you can form a triangle here. If it's going to be 0, then the answer would be yes. Okay. So the last example that I should give you is writing the equation of the line. 2 points would be given. They ask you to write the equation of the line, but using this idea. Remember, no algebra, or not algebra. Okay. So example for the equation of the line. So we want to find the equation of the line Okay, find an equation of the line passing through these points, passing through the point, through the points. Okay, 2 points, like okay, is going to be like -1 and 5, and the other one is 2 and -3. Okay, very standard problem. Remember, you have the 2 points, you create another one yourself, x comma y, and you assume that they are going to be collinear because they are on the same line. Solution. This is it. We label this one as a x1 and the y1, x2 and the y2, and you create one yourself. So this is it. So you can start with the x and the y, it doesn't matter, or just start one of these points. Okay, so this is it. Introduce x, y, the first point, x1, y1, -1, 5, and the 2 and -3. Okay, so you go with your first point, x, y1. The order is not important, of course. It's a -1, 5, 1, and the 2, -3 and 1. Since they are going to form a straight line, they are collinear. That's it. Find the determinant, let it equal determinant, the first row, x times. Delete the first row, first column. It's going to be 5 minus -3, going to be +3, minus y times. Delete the first row, second column, that gives you -1, minus 2, and it's going to be +1. You eliminate the first row and the last one. That gives you 3 minus 10 equal to the 0. So that gives you 8x. That's a -3, +3. And this is going to be -7 equal to the 0. It would be fine, but you can move it to the other side. A standard equation of a straight line. That's it, 2.3. And we are done with the chapter 2. As you can see, this section is quite a lot involved. Just read it carefully and those problems, and be ready. Not difficult, but it gets a number of the terms, the calculation of those cofactors, adjoint, but take care of this one. So we are done with the notion of the matrices. We are going to give a brief summary of the Euclidean space, Rn. If you have done calculus 3, you are familiar, but we are not going to assume anything from the past, and we do whatever we need ourselves. Okay, put them together. The practice test is coming, and then I will post the practice test and I go over it. And so this is the target of this week. Make sure you know everything by Monday. And by Monday, I give you another recording regarding those new chapter. Okay. Have a good day. Take care. If you have any question, email me. If you want to come to office hours, send me a quick email first. Then you are welcome to come at the time that we have assigned. Or if you need any other time, just send me an email. We can arrange it for you. Have a good one. Take care and